And with that, I would like to pass the presentation over to MLHC Program Chair, Ken Jung. Go ahead, Ken.
Welcome back, everyone. The next talk is, it's pretty exciting. It's a real privilege to be able to introduce Emery Brown. Professor Brown has a long list of accomplishments. He is the Edward Hood Kaplan Professor of Medical Engineering and Computational Neuroscience at MIT, the Warren Zapel Professor of Anesthesia at Harvard Medical School, and somehow he also manages to be a practicing anesthesiologist at Mass General. His experimental research has really helped define the basic mechanisms of how anesthetics work, and his statistics research has developed a broad range of statistical and signal processing methods to improve data analysis in neuroscience. He is also a member of no less than 4 national academies: the National Academy of Inventors, of Medicine, of Sciences, and Engineering. And this is going to be a really fantastic talk. It starts by asking really basic questions about what does general anesthesia do to your brain? How do we measure these things? And then how can we exploit some of these insights for clinical benefit? And I hope you enjoy this as much as I did. This is a real great soup to nuts story. Over to you, Emery.
Great, thank you. Can everybody hear me okay? And you're able to see my screen okay?
Yep.
Okay, all right. So Ken, thank you very much for the introduction. So I'm going to talk about the dynamics of the unconscious brain under general anesthesia. And let's see here. Okay, so these are some of the funding sources that I had the good fortune to have from NIH and also from the Department of Anesthesia at MGH and also from MIT. So this is what the outline I'm going to follow. I'm going to give you a clinical look at what general anesthesia is. We'll talk specifically about loss of consciousness due to propofol and other anesthetics. I'll talk about anesthesia in the aging brain, then I want to show you some things about closed-loop control of anesthesia. So let me start with the definition. What is general anesthesia? So it's a drug-induced reversible state that consists of these 4 sort of characteristics: anti-nociception, or control of pain. You're unconscious. You should not remember anything that's going on under anesthesia. So there's amnesia, akinesis, so you're not moving around while the surgeons are operating. And this is done by maintaining physiological control, stability and control of the physiological systems, right? And it's often said that it's not clear how anesthesia works, and nothing could be further from the truth. So I just want to show you a little video here just to illustrate the idea of like what's going on. So in all of our patients, we can put on 4 leads of EEG to track the brain states of patients under anesthesia. And this is the EEG of a woman I took care of. You can see it was back in 2013. And we're going to do an induction in her. I'm going to give her a bolus dose of propofol, our most used anesthetic. And you're going to just see in real time what happens to her EEG. And I'll just talk you through it as it occurs. So I'm going to play this here. So right now, you can see the EEG. And if you've not seen EEG before, those are eye blinks there, okay? And the EEG is on her forehead, 4 locations on her forehead. And now, watch what happens. It's going to start to get really noisy here in just a second, because this is her tensing up. When you inject propofol into like a small vein on the back of the hand, it burns like crazy. So the noise that you see now, that's her tensing up. All right. And now, this is actually good from a pedagogical standpoint, because you're going to be able to see precisely the second when the drug takes effect. That's about another, let's say, 5 seconds from here. Like watch right here, right? Now, you see this conversion to beta oscillations, all right? That's like a sedative state. And now she's large, slow oscillations. They're going to get even deeper here, right there. And next you're going to see it become flat and then burst, and then flat, and then burst. So what am I showing you? This is what I just illustrated. So this is her awake. She's at about 5 microvolts in low frequency, sort of high frequency low amplitude oscillation. Then she went into the sedative state. This is what are called beta oscillations, between 6 to 12 cycles per second. And if I wanted to sedate her so she could have a small procedure like a colonoscopy, that's what I'd shoot for. But the states below this, from D down through G, these are states of coma. These are states of profound unconsciousness. And we saw her go into E here, which was just large, slow oscillations. Then she went into this state here, which is called burst suppression. This is one of the deepest states of anesthesia, except for the isoelectric state, which I'm showing down here. So this is the brain being profoundly inactivated. And we're going to talk about that, later on when we talk about medical coma. And so between the burst right here, she would be isoelectric. And we didn't even see the state D. She passed right through that. But we're going to talk mostly about, that particular state there. And it turns out there's an additional state here, paradoxical excitation, which we're not going to address today. But the key point is, as you move into deeper and deeper states of anesthesia, you get these highly structured, very regular oscillations. And it's these oscillations that are impeding the communication of the parts of the brain. So this is how the drugs are inducing unconsciousness and maintaining unconsciousness. And just to give you some sense that this is like 5 microvolts here when you're awake. Then down here in these states here, which are the states of, as I said, unconsciousness or effectively drug-induced coma, these are between 20 to 50 microvolts in amplitude. And in kids, as we'll see in a bit, they can be as large as 1,000 microvolts. So I'm going to show these in terms of spectrogram over time. So this is the case of a woman I took care of a few years ago. She's 19 years of age, and she was having a small procedure. So we gave her Propofol, gave her 200 milligrams here. And then over time, we maintain a Propofol infusion, which you can see the time running on this axis here. So time here. This is the frequency of the oscillations here, and this is the spectrogram here. The colors sort of are color-coded in decibels. And the one thing that you'll notice here, so here's this large slow oscillations came on. Then after that, you see how she flipped into this state here, where you're seeing about a 10 hertz oscillation here, and also a slow delta oscillation here so this is about 0.1 to 4 hertz, and about 10 to about 12 hertz or so. So this is the classic signature of propofol in a young person. And here's what the signal looks like in the time domain, where you can see the large slow oscillation or delta oscillation and the higher frequency oscillation riding on top. So that's propofol. That's classic propofol for a young person. So you can see there's a very rich, very robust temporal signal. Now it turns out there's a very strong spatial signal as well. So we've had volunteers let us anesthetize them so we could study these oscillations. And so we're looking at the top of someone's head here, one of my subjects' head. And they have 64 electrodes, and these are 44 of those sites. And each site I'm showing you the spectrogram, kind of like what I was showing you there, coming from the front of the head in that particular person. So this is the front here, the left is over here, and the right is over here. And this is the occiput back here. So you see, there's this phenomenon called there's eyes closed alpha oscillation. So if you close your eyes and you put electrodes on the back of the head right here, you'll see these oscillations that are 10 hertz. Pretty much everybody does it. Maybe we lose it as we get older, but it's a fairly robust phenomenon. So it's literally just closing your eyes, putting electrodes on the back of the head. You'll see this 10 hertz alpha oscillation. So one of the things which is interesting about anesthesia is when you anesthetize someone, this alpha oscillation moves from the back of the head to the front. It concentrates in the front of the head, and then it moves back. And this process is called anteriorization. I just want to show you that because it shows you that even though you see this very rich temporal dynamics, there's a very rich sort of spatial dynamic taking place across the entire head. So here's the baseline. So what I'm going to do is give this gentleman, this male subject, increasing doses of propofol. It's going to go up to about 5 levels. Each level is about 14 minutes or so, and then we're going to back down. And you're going to see this oscillation here that you see in the back here. It's going to move from the back to the front, concentrate in the front, and then move backwards. So let me just play this here now. So I'll start it. So it's breaking up in the back now. So now started the drug there. So now it's breaking up. And you see how it's appearing in the front really strong. And this isn't even the deepest level. The deepest level is actually level 5. So now you can see it's level 3, level 4, and now level 5. And now what we're going to do is we're going to turn the propofol off and let the drug effects wear off. And you see how it disappears in the front and it reappears back here in the back. So what can we say about this? So I can draw diagrams like this because I know the anatomy. So propofol works by enhancing inhibition in the brain. So in the cortex and the thalamus and the brainstem, and pretty much anywhere else throughout the spinal cord. Now, so this is known anatomy. So we can just draw a picture like that based on what we know about how propofol works. You go to the operating room and you see a picture like this. You see this alpha oscillation like this, certainly in a young person, and then the slow delta oscillations like this. And now you do an experiment like the one I just showed you, and you see this alpha oscillation concentrates in the front of the head. And I'll just tell you one other little factoid about this alpha oscillation. It turns out it's highly coherent. So if you were to measure the coherence, like using global coherence or just simply taking two spots in the front of the head and calculating the correlation between the oscillations in this alpha range, between this 8 to 12 hertz range, you see that the correlation is about 0.8 or 0.9. So this led us to the idea that this must be some sort of central phenomenon sort of controlling this. And with the help of Nancy Coppell, who's one of our collaborators, mathematician at Boston University, we deduced that this is likely an oscillation. The alpha oscillation is like an oscillation going back between the thalamus and cortex like this. And why would this make you unconscious? Well, the thalamus, just to remind you, is a very important way station in the brain. It controls sensory information, visual information, auditory information, pain information. So if you were to tie it up, you would definitely create a state of unconsciousness. So that's what we think is happening. And so we've now also verified this by sticking electrodes in these sites in non-human primates as well as in rodents. But let's look at the slow oscillation. It has a whole different character. And the best way to look at it is with this new research, which we just published a few months back with Earl Miller, my colleague over at MIT. And this is from Jake Donahue's PhD thesis. He's one of our students. And so here you can see these are 4 brain regions. So 2 in the front, 8A, prefrontal cortex, posterior parietal cortex, and superior temporal gyrus. So these are 4, so going from front to back, all right? And here's what the field potentials are doing, kind of like the direct cortical recordings of like the EEG, like I was showing you in humans. And then here's what the neurons are doing. So the animal's awake, you see this very rich spiking activity, neurons spiking everywhere. Now look what happens when these large slow oscillations appear. There are 2 main characteristics here. One, you have periods of very sparse spiking here, like there, and they're quite long. And the second feature is the spike rate has dropped dramatically. So here the spike, when the brain's awake, the neurons are spiking at about 10 to 12 spikes per second. And this has dropped to about a half to 1 spike per second. So with these slow oscillations, it's actually creating what are called up and down states. And these down states are long periods where the brain is not spiking or the parts can't communicate. So this is another mechanism through which the oscillations are disrupting communication within the brain. This is important because if anesthesiologists were to use the EEG like I'm suggesting here, then when you see oscillations like this, you see oscillations like that, they can rest assured that the person's unconscious, and things like awareness under anesthesia are totally solved problems. And we could go on in more detail with the various anesthetics. So for example, we could look at them in the time domain. And one of the things that we found, it's so much more informative to look at them in the frequency domain. I showed you propofol before, but here are 3 of the other drugs. So this is propofol, like we were just showing you. And here is sevoflurane. Sevoflurane is an ether. We still use ethers. Sevoflurane, desflurane, and isoflurane are all ethers. And here's ketamine. This is low-dose ketamine. And as you see, the signature is quite different. So these guys are very similar because even though this is a gas and this is an IV anesthetic, they work through enhancing GABAergic inhibition. And so they have very similar spectral properties. In addition, this has another oscillation, which is between 4 to 8 hertz here. And that's something we're investigating. We don't quite understand why that's there. But if you look at ketamine, you can see low-dose ketamine. This is the sort of like the dose range in which someone taking ketamine will hallucinate. And what you see here is that it's at 30 hertz as opposed to maybe down at, between 8 to 12 hertz, like with propofol, all right? And this is dexmedetomidine, which it produces very, very profound, like slow oscillations. So we can do the same thing with these drugs, like I did with propofol, doing, detailed study of the oscillations, looking at the anatomy, linking it to the anatomy, the neurophysiology, making inferences about how they're working. So this is sort of a kind of a main part of our analysis, our research, but it begins by doing detailed analysis of the structure of the oscillations so that we can then go and try to do neurophys that helps us understand how the oscillations are coming about. And as I said, the oscillations are not an epiphenomenon. We think they're part of the fundamental mechanism through which the drugs are inducing altered arousal states, in particular like unconsciousness. So let me show you what happens to the brain as it ages. So this is a 30-year-old under propofol anesthesia. Looks just like the one that the 19-year-old woman I showed you earlier. You can see the alpha oscillation, the slow delta oscillation. Here's a gentleman who's 57. Like this guy here could be like his dad. And you can see the alpha oscillation. You can see it's shifted down a little bit. So it's shifted down relative to where it was up here for this gentleman here. But it's still there. You can see it a little fainter, but still there. And you can see the slow delta oscillation here. Now here's the same thing in a woman who's 81 years of age. She has, you can see her alpha oscillations here. You can see her slow delta oscillations. They're much weaker, and this is very typical with aging. That is, the oscillations get to be much, much weaker. And one of the key features of this is a woman that I was taking care of. She was having surgery in which they were removing a tumor the size of an American football from her chest. It took the thoracic surgeons, the better part of 6.5 hours to do that. But I was able to give her like a fraction of the already age-adjusted dose of the anesthetics to keep her unconscious because I was monitoring, her brain activity. And one of the things which is important to notice, not only is there, there's a complete absence of the oscillations up here in these bands where you normally have sort of, again, like the high frequency oscillations that I was showing you that she was conscious, in addition to having the appearance of these like the slow oscillations and the alpha oscillations. And the reason that the oscillations get weaker as we get older is that you can think of this as sort of the fidelity with which the neuron can transmit the electrical signal. So as neurons get older, the myelin sheath breaks down. Remember the covering across the neuron. The dendrites don't extend and retract as much. You don't produce as much neurotransmitter. The cell is much more vulnerable to oxidative stress and injury, and the mitochondria don't work as well. So essentially the wiring is becoming frayed. So her wiring has been around for 81 years. So it means that it's not going to transmit the electrical impulses as faithfully. And one of the things to appreciate about that, it doesn't take so much propofol or anesthetics to render her unconscious as a consequence. And so that's something you should always take into account. Now here's the part which is a little bit sobering. So his EEG looks like his, but this guy here is roughly the same age as this guy. His EEG looks like hers. So we age different physically. It makes sense that our brains age differently. And that's basically what we're seeing here. And by using EEG, it's interesting, you can see it under anesthesia. And if you think about why that's the case, it's because we're putting in a stimulus here, and then to some extent, based on the integrity, I'll just use the term loosely for the moment, of your brain circuits, you respond a certain way. And how you respond probably reflects, some degree of like your brain aging. And you can probably guess what the kids look like. So here's a 3-year-old. Here's a 14-year-old. You can see we have the same general pattern across the different ages, but the spectral bands are much broader here in the younger kids. And so you use the same concept, but you have a different sort of dynamic or sort of appearance of those dynamics in the younger kids. And this has to be taken into account when you're building algorithms or whatever to monitor brain states of patients under anesthesia. So I just want to share with you a few ideas about closed loop control. These were 3 very well-known people who had head injuries, and they were placed in a medical coma. So what's a medical coma? It's this very profound state of brain inactivation in which you administer an anesthetic like propofol, and you keep the person sedated for 24, 48 hours, maybe a week, or maybe even several weeks, in order to allow the brain swelling to go down or to stop intractable seizures. And now you've seen all that you need to know to understand about what medical coma looks like. You add propofol until you get a pattern like this one. And we saw this one appear in the induction video. This is that state of burst suppression. So you maintain the state of burst suppression. Now this is done manually now in pretty much all operating rooms, around the world. So we've been looking at this, using it as a way to build a control system. So we tested it out in rats. So this is work we did a few years back. So you set up a target level, a standard control system setup. You set up a target level that you'd like to have for the brain. you measure the difference between where the brain actually is, and that tells your controller how to change the infusion rate of propofol into the rodent. And your information about the brain state is coming from this estimation of the EEG signal and characterizing the extent to which you're in burst suppression. So burst suppression is kind of easy to define. We can think of it as we can think of the fraction of time in a suppressed period. So if this is 1 second of time here, and I have a little stretch here where it's suppressed, and that's about 0.4. I have a little section here where it's suppressed, that's about 0.2. So then 0.2 plus 0.4 over the total is about 0.6. So this would be a burst suppression level of 0.6. So that's our target. That's what we want to control. So I'll just show you some still shots of this. So here's an illustration of it, where the target here starts at 0.4, goes up to 0.7, and goes up to 0.9. And the black line shows you how well it's tracking. And then what you have down here is the pump, okay? And if you look over here, so it's actually easier to see if we look at it starting from this one up here. So you're here at 0.5, you go up to, let's say, 0.9 again. And now what happens is, to decrease the level of burst suppression, we don't have something that turns the system off. What the system does is shuts the pump off. When the level of burst suppression drops adequately, the pump shuts back on and continues to control the signal at the level we'd like to. So this sort of closed loop control is certainly feasible. And if ever there were a time that a controller would be useful in the case of medical care, it's certainly in these situations, because you're going to keep this patient in these states for at least several days and sometimes several weeks. But let me show you what we're working on now. Because the idea would be to eventually be able to use these systems to take care of patients. And for that, the FDA would like to see more testing in large animal models. And so we have the same paradigm set up in a non-human primate. And this is work which is done by one of my fellows, Suresh Chakrabarty. And we have the same idea. So you set up a target level. This stands for marker of unconsciousness. And you have your estimated marker of unconsciousness. Your controller compares the two and then changes the infusion rate of the pump, which goes into this is a non-human primate. And every 20 seconds, it has a 20-second doodle cycle that it uses to update the pump infusion rate. And so again, a standard sort of control setup. And now the key thing is, what is the marker of unconsciousness here? Now this goes back to what I was just saying a second ago. Remember, I pointed out that when the animal was profoundly unconscious, we saw a very profound drop in its spike rate, and that's what we're seeing here. That correlates very tightly with the power in the 20 to 30 hertz band. So this is readily observable. And since this tracks this quite well, that's what our experiments have told us. We're going to use this. We're going to build a marker that's based on the power in the 20 to 30 hertz band. We're going to control this, so we can control this. But we know that when we control this and keep it at a fixed level, that the animal is going to be profoundly unconscious. So let me just end with this little video here. So we set the marker at 1, so that's an appropriate level of unconsciousness. And what we're going to do first is just put the pump on a continuous infusion rate, just like we typically do in the operating room. All right? And then after it's on there in that for a while, we're going to let the controller take over. And so this is where the marker is. You're going to see the infusion rate shown here. This is the error. And you'll see the spectrum down here. So I'll just play this. So this is it's running at a constant infusion rate. You can see in the middle panel. And the marker is going all over the place. It's not controlled at all. Now we're going to turn the controller on. Right here. So the controller comes on. And now the first thing it does is it shuts the infusion rate down for a period, so it can capture the marker. It captures the marker at the level it wants it to be, and now it's holding it there. And now what we're going to do is we're going to drop the marker down again. We'll drop it to a little lower level. All right. So meaning the animal is more unconscious. All right. So it drops down. And so we're holding each segment for about between 30 to 40 minutes. All right. And then finally, what we'll do is we'll jump it up to a less anesthetized area. So it went from 1 to about 0.9. Now we're going up to about 1.1. And that's where it stops there. So you can see that here, right? So these are the main points that I've made. The brain under general anesthesia is dynamic. It's not turned off. It's these oscillations which we think are a major way through which the drugs are working to create these altered states of arousal. You can easily see the oscillations on the EEG. They change systematically with drug class, drug dose, and patient age. And they provide a principled way to track brain states of patients under anesthesia. I've shown you that closed loop control is very feasible. And then an important subtext of what I just said here is that general anesthesia is an underutilized paradigm for studying how the brain works. So I'll stop there. Thank you very much.